Welcome everybody to the webinar this morning or in the afternoon if you're in Europe. Apologies for the delay. Today we're going to be taking you through a topic on strategies for creating AI-ready chemical data, sponsored by the Informatics Alliance. My name is Mary Beth Walsh. I'm the founder of one of the companies in the Informatics Alliance called Collide, and I'm here today with several of my colleagues to present the content. So on the webinar logistics, the session's being recorded today. You will receive a copy of the slide deck and the video recording after the meeting. We will keep your phone muted throughout the presentation. Feel free to enter questions in the chat window. And we've set aside some time at the end to answer your questions. We may be out of time for that now, but we will try to follow up with you after the webinar if we don't get to your questions today. About the Informatics Alliance, we're a small group of dedicated chem and bioinformatics experts that focus on supporting our customers in their research informatics journey. Many of us provide professional services in life science, agricultural, and chemical industries. We're 6 different companies. Our logos are listed here. We're international. We've known each other for about 20 years on average. We operate independently, but we partner very often and share experiences and expertise, often joining forces in larger enterprise scale projects, benefiting our clients from a wide range of experiences and various locations. For more information about us, you can visit the informaticsalliance.org. Okay, I'd like to introduce our hosts today, Gerd Blanke and Thomas Doerner. Gerd, do you want to give a quick hello?
So, thanks for the invitation. I've worked for a company called MDL and Symix for 20 years, became independent since that. And with that background, you find the reason why we just know each other, because most of the people within the Informatics Alliance have got a very similar background to that one. My interest in today's topic has grown up for the last few years. I have much more a reaction background in the current moment, which we presented already at the last SAS4 meeting. And next again for the next one. And so I'm very keen to get the discussion on today.
Okay, so I'm Thomas Doerner. I'm an independent consultant in the research informatics area. My background is also many years ago with MDL, and even before I did a PhD in organic chemistry. And since about 10 years, I'm independent, helping my clients in research informatics projects and chemistry data management with various tasks like business analysis, QA, subject matter expert support, and so on.
Andreas?
So I'm a director for Digital Life Sciences at Innovation Campus Berlin, but here today I'm actually in my capacity as an academic. So I've been in the chem informatics area for 10 years, dealing with chemical and biological data. So I would like to share my experience on that.
Great, thanks so much. And Esben?
Yeah, hello, my name is Esben, and I'm originally from Denmark. I have various backgrounds from academia and industry, and also as an independent consultant. And right now I work as principal scientist at AstraZeneca here in Sweden. So I have a large interest in chem informatics and also how we can use deep learning for chemical problems.
Great, thank you. And Ted Slater from Elsevier?
Hi, everyone. I'm Ted Slater. I'm a senior director at Elsevier. My background's in molecular biology and computer science, and I spend most of my time doing knowledge engineering at Elsevier over pharma R&D type applications. That's me.
Great, thank you, Ted. Okay, so moving on to the topics we'll be covering today with you. So the topic of the webinar is on chemical data. So first is, why do we want it to be AI ready? What are some challenges in creating AI ready chemical data? How do you create criteria for AI ready chemical data? How to capture AI ready chemical data? And in addition, how to make existing chemical data more AI friendly. And finally, closing with some recommendations for improving chemical data quality. Okay, so the agenda today, Thomas is going to start us off by setting the scene for the panel discussion, which will follow. Then you'll have a short presentation by each of the panelists as we work through the topics discussed. The panel discussion will be moderated by Gerd Blanke, be 15 to 20 minutes, and then we'll have a Q&A, summary, and closing. Thomas, I'll turn it over to you.
Okay, thanks, Mary Beth. Next slide, please. Okay, so what I would like to do within the next 10 or so minutes is to set the scene and provide the context for the discussions we will be having, and give a little bit of background on artificial intelligence and the chemical data to be used in artificial intelligence. I think we are all aware that machine learning and artificial intelligence have become quite important tools to help solve challenges in many different domains, including science, and also in life science and chemical R&D. There's quite significant adoption. AI is one of the key drivers, and some people even say there's kind of a AI hype in life science and chemistry. Examples of application of AI ML in life science and chemistry include drug discovery, toxicity prediction, automated synthesis planning, and a few other topics. And I've just more or less arbitrarily picked two publications, one a bit more compound focused on drug discovery, and the other one a bit more reaction focused on chemical reaction prediction. Next slide, please. But there are also a number of challenges if you want to apply artificial intelligence. One slide back, thanks. Yes, on the right-hand side, you see a very simplified picture. You have data, and then you use the data for AI. So the basis for all AI is the data which you use, and typically this data is not necessarily ready for being used for AI ML straight away. For instance, you have heterogeneous sources with different data structures, different formats, and you also have very varying data quality. So as a consequence, there are various operations required on the data before you can really use the data for AI ML, and quite complex data running is typically necessary before you can really start. And scientists do spend quite a lot of their time on kind of wrangling with the data and preparing their data instead of using the data in AI, building models, creating knowledge from it. On the right-hand side, we see a little graph which I found on the internet. You can certainly argue about the percentages, but I think we all agree that probably data scientists want to spend more time on dealing with AI and building models rather than on wrangling with the data. Next slide, please. So just before I go a little bit deeper into the data used for AI, just one few more words on the Informatics Alliance and what is our relationship with AI ML. As Mary Beth has mentioned in the introduction, we are a small group of independently operating chem and bioinformatics expert companies, and we provide a number of services related to capture and management of chemical and other research data, starting from business analysis via data management, subject matter expertise, and so on. So overall, we are quite heavily involved in the data that forms the foundation for any application of AI ML in chemistry. And in our role, we see ourselves as advocates which have the whole value chain of the data in mind. So not only the capturing of the data, but also the later use, for instance, for artificial intelligence. So we think of possible downstream uses of the data, such as AI ML, right from the start, and we have an eye on the whole data life cycle. So we are basically sitting at the basis of AI and ML. Next slide, please. In the following, I want to go a little bit deeper into what I mean with chemical data and AI, and set the scene, highlight a few different aspects to set the context for the panel discussion. Of course, within the few minutes, this is not aimed to be comprehensive, but should only give a kind of rough scratch on the surface. So if we look at the data life cycle, as you see on the graph on the right-hand side, usually starts a little bit before the data comes to life. It starts by creating the data capture framework, for instance, setting up an ELN, defining the fields, what data you want to capture, how you want to capture the data, and so on. Once the framework is set up and the framework has gone live, then the system is productive. You capture your data. In due course, this data might get transferred to data lakes, data warehouses, other systems. Over the life of the data, the data might be converted and migrated to even more other systems. It's spread around, moving around, disseminated, for instance, to cooperation partners, going into the public and so on. And at some point, it may become legacy data, which is still around, but it's not really fully supported anymore, not migrated to newer systems and so on. And at all of these stages, the data can potentially be used for artificial intelligence and machine learning. There's quite a number of disciplines involved in this whole life cycle. Data creators like research scientists and technicians, but also data consumers like data scientists, and also a number of supporters like software vendors, solution providers, and also consulting companies like the ones in the Informatics Alliance. Systems involved, just to name a few, is for instance the ELN, the electronic lab notebook, registration systems, but also systems where you capture and track your biological activity data, PK data, admin-tox data, and physical property data. There's data lakes and data warehouses involved, and there's also public databases involved, which you can use as a basis for AI/ML external files, for instance, SD files to get from any CROs working for you, data which sits in software as a service solutions in the cloud, and so on. Next slide, please. Chemical data, it's basically can roughly be divided in chemical compound and chemical reaction data. So chemical compound data is mainly 2D structure data, and you face issues like salts and protonations, tautomers, and different formats. There's 3D crystal structure data, and there's related data such as purity. On the reaction end, you also have things like mapping, which you need to consider. And you have, in addition to the actual reaction, you have data on agents, catalysts, solvents, reagents being used, data on reaction conditions, and data such as yield. Then in the context of chemical data, you have also other data, which is not in the narrow sense, not really chemistry data, but is, for instance, biological assay data. So you have classic numerical or nominal data and classic unstructured data like free text fields or documents and attachments. And you also have metadata giving context to the data, like information on protocols, conditions, instruments used, administrative metadata, owner date, and so on. And ideally, you also have captured metadata about the life cycle. So what has happened to the data in the course of the life cycle, data capture, degradations, fixes, transfers, and so on. Next slide, please. So very basic requirements for AI and ML for the data are that somehow the data must be available, machine readable or machine ready. It should have been converted into the same format. It should have been normalized, standardized. Normally in the process, you will convert the data into a flat table format, and in many cases you will also have or create some target variable, which is kind of Boolean like my chemical reaction has been successful or has been unsuccessful. There are also some higher level requirements which more apply to the data set that you use as a basis for AI/ML, so things like set size, any bias, and so on. I think this will be quite a bit of the topics of the discussions to follow. And the actual requirements for the data also depend to at least a certain extent on the actual use case, of what kind of AI you want to apply and what problem you are trying to solve. On the right-hand side, we see kind of an abstracted workflow, and not necessarily in the given order here, but I think it at least gives some idea. Quite often you federate data from different sources. You select the records which you you want to include in building your model. You clean the data, you merge, aggregate, and deduplicate the data. There may be some abstraction steps, for instance, classification like a successful, unsuccessful reaction. Then you massage your data into flat file format. You divide your data into training and test sets. Then based on that, you build your model. And once the model has been built in quite often a number of iterations and you're happy with the model, you deploy and apply your model. Next slide, please. So this brings me to the end of the talk. I hope I have been able to give some context to the discussions to follow and set a bit of the basis for the presentations from our 3 panelists. So thank you very much, and on to the panelist presentations.
Great, thanks so much, Thomas. So now we're going to move to the panelist presentations, and we're going to start with Andreas Bender. Andreas, do you want to take it away?
Sure. Yeah, so the emphasis I would like to put on data is, as Thomas outlined before, of course, we need to make sure to structure our data properly and so on. But the first question I would like to ask is, and that's the scientific angle I would like to offer here, what's actually the data we need to answer relevant questions? And relevant in the sense of drug discovery in this case, efficacy and safety in the clinic. So what is actually data that gives me predictivity for the in vivo situation? How do I actually annotate that? And that is very tricky. Chemistry data itself is tricky enough. You have different conformations, tautomers, and so on. But if it comes to biological endpoints, quite often those annotations are even more tricky. And on the next slide, I'll outline some of those aspects. Yeah. So what is actually the data we have, especially in the pharmaceutical context? If we think back, drug discovery 60 years or so, historically drug discovery in times of James Black, that was more phenotypic drug discovery, right? His antihistamines, he made 20 or 30 compounds, tried them in pigs, right? And that was drug discovery. Then we had the biological revolution. So we now can express biochemically, we can express any protein we want in assays and so on. So we then had this revolution of high throughput data generation at the cost of simpler assays. Yeah, and this is quite often the data we are stuck with currently as well. So there's quite a lot of proxy assay data we have right now that is actually not meant to be historically to be endpoints in themselves. Yeah, these are simple endpoints, high throughput endpoints, which we can determine, which are meant to support decision making in context. Yeah, but quite often the data we have, especially in companies, but also from public sources right now, they're actually assembled more or less by accident. Yeah, so there's quite often no experimental design when it comes to chemical space coverage. So what does that mean, for example? So if you want to see if you want to test, for example, particular compounds in an assay in order to generate a machine learning model, quite often the compounds that get put into those assays are project compounds. Yeah? So there's no experimental design in which compounds get tested in order to generate models. And also the endpoints we have, quite often they're of proxy nature. So they're meant to inform decision making historically. So they are not endpoints in their own right. And so that is the data we actually have. So it's still the legacy, so to speak, of using proxy data, high throughput data that gets generated and that gets repurposed right now for AI in drug discovery. But that might not be in all cases the ideal data, right? Because usually we need to understand what is the question we ask, what is the data we need to answer those questions related to safety and efficacy in the clinic, right? And then there's the question, how do we annotate that data? So right now the situation is quite often the data gets repurposed, and so it's proxy data that was meant to support decision making that gets used and put into models right now to generate machine learning models. So that's the data we have right now. So it's generated historically, not so quick maybe. What, was it too long? Or maybe that's a subtle hint. Yeah. So the data we have is, okay, yeah, maybe let's start here, it's fine. Yeah. Yeah, so that data was only meant to support decision making. Yeah. Let's see, I'll just wait one thing. Okay, yeah. Yeah, and so that data was meant to be used in the context of a project and the overall and the overall compound profile, right? So you have a compound that you dose in men at a given dose, and that is used in a particular therapeutic area, right? And so, for example, there's data on certain toxicity assays. Let's assume that's my favorite assay here, the glue-gall mitotoxicity model. In some sense, it doesn't matter what that assay is, but the point is that is an assay that covers one aspect of mitotoxicity, right? And someone who's a project chemist, for example, would understand the limitations of that, right? And the danger is we take that data, put that into a predictive model, and that is then something we label mitotoxicity, right? But it's only one aspect of mitotoxicity. So I'd like to point out that it's very important to understand the difference between proxy assay endpoints and the actual endpoints we're interested in, and that is often organ risk, let's say, and not the proxy, so the particular assay endpoint. Yeah, and so it's important to have hypothesis-driven data we generate, as well as data that is generated not by technology push, but by scientific pull. So to generate the right data for the right purpose that is predictive, and that is visualized on the next slide. So that is a pyramid of how ideally one would generate data, right? So at the bottom of that is a question or hypothesis. So what are the key parameters that tell me, let's say, whether a compound causes liver toxicity, right? And then the data I generate might be gene expression data, and I understand that a certain gene upregulation of a gene is linked to DILI, for example. And I represent that on the gene level or pathway level. Yeah, and on top of that, I put a computer science method. But the whole method, the machine learning method, is based on a representation that is based on data, and well as which is based on a question or hypothesis. And so this is the perspective I would offer here. And it's very important to have the right data for the right purpose, which then of course needs to be annotated with, for example, controlled vocabularies and so on, in order to then perform machine learning. But don't forget the data, the question, and the hypothesis, yeah, to generate the right data for the right purpose. Thank you.
Great. Thank you so much. And moving on to Esben with AstraZeneca.
Yes, thank you. As I said before, I'm from AstraZeneca. So let's dive into the slides. Next slide, please. So I work in the molecular AI department. Sounds fancy, and we provide some algorithms and tools for drug discovery projects. And there are two questions we want to answer with these tools and make more efficient. And one of them is what to make next. And the other one is how to make it when we have determined what is we want to make. So for the first question, we have had a lot of success with de novo design of compounds. And there we typically use long short-term memory networks and SMILE strings. So here, AI-ready data is simply a list of SMILE strings of compounds. So of course, we still need normalization and standardization and such things, but we don't need much more than actually knowing the structure of the compounds. Then in contrast, we also have retrosynthetic planning. We use some other algorithms there, neural network powered Monte Carlo tree search. And there we have a lot more demands on what we call AI-ready data, because we need atom mapping of reactions, and that's not necessarily a well-defined mapping you have in all instances, and you need to apply it to new reactions, and you need to do it from different data sources. Another thing is that there is also a big bias in the data set between reaction types. Some reactions are used much more than others. And that's also something we need to counteract. And we need to know about protection group chemistry. When is it protection group? And every chemist can see that, but it's often sometimes just omitted when we have the reaction annotated in the database. Then also what we have been looking into is negative data. And that's actually also a point a lot, especially in reaction, is that you report the reactions that work, whereas the ones that don't work, they can not work for so many different reasons. Example, it can be a yield of 0, and then it says in the common field that the experiment were never conducted. So there's often a lot of cleanup of what we consider negative data. It's a negative data because it was tested one late afternoon, and then the chemist's spouse called and asked to pick up the kids, and then it was terminated early, or was it 3 months by a really hardcore chemist tried to do this that really should work, but just don't work in practice. I mean, it's different levels of negative data. So next slide, please. So what we're doing also is we're living in it. We need to collect different data sources. We have this project where we have a central data repository we call Reaction Connect, where we get different data. Now my slide disappeared. We get different data from different files from our medchem, from different ELNs, from in-sourced reaction data from Reaxys and Pistachio database from Nextmove software, and also open public access data from USPTO dataset on reactions. And then we have all these different sources, and we need to extract it and put it in a common thing, and we need to normalize it, and we need to have all the normalization and atom mapping and role assignment and check up on the data. I think there is a little bit missing from the bottom. But anyway, next slide. So what I actually wanted to say about this is that this is a project that we have been working on for quite some time, and we are still not finished getting everything into the data there. One thing here, the last slide, I'm actually echoing Andreas a lot here, because we have this data collection bias, as he pointed out. So we often collect it as a side effect of projects, and therefore there is an enormous bias in the data. And therefore, I think we need to also have a mental shift there. And it can be difficult to actually achieve this, but we need to start to harvest the data for the sake of AI and machine learning. And I think automation will really be the key there, because then we can do a higher throughput there, and we can have more consistent conditions under which we get the data. So active learning strategies is also an interesting field there. Can we do something to select what compounds to test next, and therefore maximize our information gain from each round of synthesis and testing that we do? So I'm finished there. So let's go to Ted.
Great, thank you so much. And moving on to Ted Slater with Elsevier.
Yeah, thank you. So next slide, please. So I would just like to talk a little bit about FAIR data, but I'll preface it by saying that the problems that we're talking about here in preparing data for AI and basically any kind of application, to be sure, are very real, and they cost a lot of money all the time. And this is just one famous example from Novartis, where they made a big commitment and a public commitment to do some work in AI, and when it didn't go quite as far as they liked it to, they pointed specifically to this problem of data and getting it ready for AI. That's why we're having the conversation today. But just to point out, it really can take a lot of time and money. And interestingly, even when we have seminars like the ones we're having today, it comes as a surprise to a lot of people when they're trying to get ready to do this work, and they find that they're quite a long way from being able to get started. So how do we address that? And that's where the next slide comes in. Thank you. So the way that we're trying to help out in this space at Elsevier and in other places is through FAIR. And FAIR is just the FAIR principles that many of you have probably heard about. FAIR is an acronym that stands for findable, accessible, interoperable, and reusable. The goal of FAIR is reusability. There are a couple of parts in there that are pretty hard, and I think there's a big contest between the F part of FAIR and the I part of FAIR to see which is the most difficult aspect of FAIR to do. Is findability the hardest, or interoperability? So it's an interesting thing. What we find out there when we speak to people who use Elsevier's content is that they are making the same commitment to FAIR data that we are. The benefits of FAIR are many. It certainly makes data integration and interoperation, including federation. So if you don't want to put all your data in one place, FAIR can make that easier too. So all of those things become easier with FAIR. data are ready for almost any purpose, not just AI. So AI is very important, no question about it, but there's still a majority of use cases out there in all our fields that are not AI, but they're things that we've been doing for quite a long time. And that actually prompts me to say that the principles that are in the FAIR principles are mostly not new. They've been around for quite a long time, and people who are data stewards have used them for a couple of decades now, really. But FAIR as an acronym and FAIR as a set of principles written succinctly is quite new. And I think as more and more people understand what that is and have a good handle on how to deal with them, we'll see more and more of it. It also, if you use the FAIR principles, enhances communication and sharing of chemical knowledge and other kinds of knowledge. So I think that's quite important, and we're seeing that as well. And it helps keep data separate from systems. So what we keep hearing more and more is that our customers and other people want to focus their attention on the data themselves. Those data can go into multiple systems. You don't want to just create data for one specific system or application and leave it there and not use it for something else. So the idea is focus on your data first, clean that up and make it reusable for all kinds of things by application of FAIR principles. And then whatever system you need to put those data into, you can do that. So Esben, for example, showed a picture of Reaxys data going into Reaction Connect, which is a system they're putting together. Our responsibility in creating Reaxys is to make sure that Reaxys data are interoperable not only with other Elsevier content, but with anybody else's content. We want to make Esben's job easier. So that's what we're working towards. Next slide, please. Thanks. So it's actually pretty difficult to do FAIR a lot of times, and it's important that people understand that. The good news is that FAIR is a spectrum. There's not just one single bright line that you cross in order to make your data fair. So what that means is, and this has been mentioned a few times in our presentations already today, you can decide what your data are going to be used for a particular purpose and verify those data to the extent necessary to handle that use case or use a set of use cases. So I think that's important. You can build on the work that other people have done to make it easier for you to get to a FAIR level that you're comfortable with, and that's what we would advocate. There's a lot of help out there for people who are trying to do FAIR. It's not easy, so you shouldn't feel bad about asking for help. There are lots of people who have some experience and can help you through it. The Pistoia Alliance is certainly one of these organizations that has some projects ongoing in FAIR, and you can be a part of that. There's also the Go FAIR organization out there, and they have their CHIN network that you can use to help with FAIR. One of the really important points here, though, is starting with FAIR data whenever you can, and hopefully whenever you can is as early as possible. So one of the things we talk about in the FAIR ecosystem is your data are better born FAIR. The sooner that you verify these data, the better off you will be, and the more interoperable they'll be for your purposes. And I think I'll stop there. Thank you.
Okay, great. Thank you, Ted. And moving on to our panel discussion moderated by Gerd Blanke.
Yeah, so thanks to all of you joining us. And I think you gave a pretty good scope of how machine learning and AI is used in research, and with major focuses, of course, to pharmaceutical development, as well as in the current moment in terms of reaction optimization and prediction, which is actually the base, for example, of Esben's work for the further steps that may go along in the foreseeable future over there. But let me start with Andreas. So basically, you said on the more or less on the biological side and towards clinical data, it's impossible to have AI-ready data because we are just working with the wrong model. Yeah, so instead of working with the real disease model, we're taking the model of that one, for example, that is transformed over to an assay. And then we take the assay data that we start to squeeze in AI with AI methods. On the other hand, I'm started to get the question, how do you see how the real AI working with the disease, for example, could look like? What type of components have to go into that one? And how can you train those types of models?
Yeah, I think what is important is to understand the predictivity of the assay endpoints we have. Yeah. So, for example, in DILI, yeah, that's probably one of the safety endpoints that is most explored or understood right now. Yeah, but even there's no agreement on DILI annotations for some compounds. So I think what you need to understand is, so what is the predictivity of different endpoints? Yeah, different assay endpoints of different aspects, for example, of safety. And for those endpoints, yeah, you have a good experimental design, coverage of chemical space, yeah, and you understand what is the mechanism covered and what is the chemical space covered within those mechanisms that then all together, yeah, give you an organ risk predictor, yeah, that also depends on dose then, right? So you cover different mechanisms. Within those, you have experimental design on the chemical space. You understand predictivity of the endpoint, how that translates into the clinic, yeah. So you have different blocks basically that cover different aspects, and within those blocks, you need to do experimental design. I think that's the best answer so far I could come up with, yeah. But I think right now that is hardly ever the case, yeah, because right now it's quite often biased or project data, and this experimental design and understanding what is the predictivity of the individual endpoint, assay endpoint for the in vivo situation, that is also not sufficiently explored. Yeah? But I think that would be necessary. And once you have that, then you can annotate your data according to ontologies or controlled vocabularies, right? Do experimental design and build machine learning models. But we need to understand first what we need and generate that data, yeah, in many areas, yeah, before we then build models. I think that comes later. Yeah? First, we need to care about the first step, in my personal opinion. Yeah?
Having Ted's talk in mind about fair data, would that help as well, especially if you, because you mentioned as well, the chemical space of one company has to become too small. You have to just develop your models using as many data that are available. And with that one, it becomes more and more important that you have comparable data sets. Would fair way to set it up?
Yeah, but only if you have experimental design as part of the process. Yeah, I mean, yes, fair is one aspect, but if you don't design, I think you need an IMI consortium, yeah, across industry, let's say, but also for design. Yeah, so not only pooling what is there and everyone puts together whatever we have that in the cupboard. Yeah, here you use that. Yeah, that is not the right data for the right purpose. Yeah, but if you include experimental design in that, and then the data is fair. Yes, is a short answer, yeah. But you need experimental design, I think, in addition to having fair data, yeah, across industry in an IMI consortium, let's say.
Yeah,
I think.
Where the experimental design in the current moment seems to be not that well discussed from what I followed up. And it's much more an issue for the upcoming next steps where companies have to work closer together if they are allowed to, because it's always, of course, a question of competitive situations.
Yeah, it works only in pre-competitive areas. I agree with that. But even there, I think there's more that can be done. I think so.
If you come over to the chemical point of view or directions, do you think that AI data are easier to achieve in that area? Because the way how chemical structures are described is well, pretty much traditional, and they offer a lot. And as Esben said, you know, it's a smiles. And then from there, we do our predictions. So somehow within your talk, I even see, you know, two words a little bit. Yeah. So the chemical space that is better defined, not well defined, but better defined. Then, and of course, the biological data that are much more diffuse. Do you think in that case that for the chemical area, do you see there major hurdles to prepare data?
Yeah, I mean, usually you have endpoint annotations, right? And bias sampling, because that's one of the things Esben alluded to as well, right? I mean, your endpoints can be biological, but even if it's synthesis, right, you have biases when it comes to, for example, a positive example bias or so, or various other biases, yeah, or analog bias and so on. And so that is a problem in that area, I guess, as well, yeah. And if biological endpoints come into play, what I said applies in addition to that, yeah. Even in the chemical area, the sample bias and so on, that does exist as well, yeah.
To Esben, just because thinking about the endpoints in terms of reactions. Yeah, so what you have described is, the full broad range of where the different reactions come from LabJournal, from traditional databases, like, for example, Reaxys, or from Nextmove. And on the other hand, all of them have got different rule sets. All of them have a different way to normalize. So what I see on your side is a big bunch of work just to get a foundation that makes those data ready for further steps. Have you automated those processes? Have you implemented all those processes meanwhile, or what is your current status?
Yeah, that's why it takes a while to get this to run. Luckily, we didn't wait for the final database before we started using the data. So it has been some years where we have had like 2 tracks. We have had the work in my team, our department, with various flat files where we sit and just make it ready to test if our AI will work with it. But then we have also had this more structured approach to it, where we will have the data that we can relate back to in the production systems. So then when the AI comes and make a prediction, we can link back to the original template and say these came from these reactions, from these patterns or these literature sources, and show this to the end user, which creates a transparency to the data, and also works as a very good lookup of the actual conditions and the closest reactions there. So that the chemist can take a decision there. This suggestion is actually close enough to the literature data that I think it will also work in my instance and maybe have a good starting point for the conditions. But yes, they come in very different shapes and very different levels of maturity and fairness, and very also completeness on annotations with, as example, conditions. And other notes on each reaction itself. It's not just the reaction smiles that is going into the database. It's also all the other metadata around it that is necessary to actually understand the reaction there.
Have you created some type of standard within the company where you say, okay, if you just capture a reaction, please enter following fields? Where, for example, you gave a very good example about the failing reactions. You never know whether it was just the weekend that came in or it was a hard work somebody put into it. Any way to control that and to find out what is happening behind that one?
I mean, there is certain consensus between various data sources about what should be there, right? But we also need a consistent way of having this. So that means a lot of the things we need to go through systems again and redo the atom mapping in a consistent way across all the different databases, and not just rely on the atom mapping that may already be there by various toolkits or various ways of doing it. So that is a ETL pipeline we are putting up, but it needs customization every time we get a new data source. And also every data source simply needs to be examined to find various inconsistencies in the annotation. I mean, the ELN was not created as a data harvesting tool, but rather a notebook for chemistry work. So it's not always they're set up to be capturing data in a very consistent way. So sometimes there is abbreviations of various coupling agents or other things, or there are simply codes that go in there, or people draw the molecules in a bit different way and such things. So there's a huge work actually to take each data source and take it out and make it ready. So that's where some of the in-license tools are. There is a lot of the work already done, right? But then it's done in a different way in the 2 different data sources that we want to use anyway. So you never really come around it, I think. That you need to look at the data yourself. And also, it also really depends. I mean, what is the purpose of this, right? For this Monte Carlo tree search thing we are very dependent on, as example, the atom mapping. Whereas various other deep learning approaches with transformer models, they don't need that. They create it on the fly, so to speak, from learning from the data. So it also really depends on the application, what is needed there. Another example is condition prediction. Also, where we try to use the conditions of various sources and predict what is the optimal, or what is a good suggestion to start out with there. And there, of course, you need to have the conditions annotated in a good way, but there's also time-wise drift in there. So we're always behind that because chemists tend to like the ones they just read about that was optimized in a paper, and not the ones that actually would work but were fashionable 3 years ago. So I think it's a never-ending story, and you need to work with the data, and you need to also do that as part of your AI projects. We can probably help and make that easier in the future, right, by verifying the data. But I never think we'll get to the point where for any application you can ever imagine it's just ready. No, I think that's.
And if I see, thinking about your work, it must be the same work Ted has to do, or what Reaxys has to do, to clean the data. If I think about that, you've got more than 200 years of chemistry in the database. That means 200 years of research, 200 years of different ways to look into structures, 200 ways to clean up, which is a tremendous amount of work. How can you do that?
Pieces. We break it into pieces and do what we can. That's why it's so important that FAIR really is a spectrum of things, and you don't need to apply every FAIR principle at once. So one of the reasons why the F part of FAIR, the findability part, is so hard is because of identifiers. Just trying to put a name on entities that you can use across different data sources and things is pretty difficult. But now we're getting to a point where we can extract FAIR identifiers from other sources, like from the EBI, for example, and use those across different sources. And we also have, I guess the way to put it is, knowledge graphs have advanced to the point now where it's pretty easy to associate all kinds of synonyms, for example, to those identifiers that you're trying to use. So if some lab uses one name for an entity and another lab uses a different one, you can still associate those with the same identifier and make a lot of progress quickly. So that's how you do it. You do it in the pieces that you need first, and then you go forward as you're able.
Because of the time, I think unfortunately we have to stop the discussion over here.
Yeah, thank you, Gerd. I think this has been a really good discussion. We do have a minute left. We do have a couple of questions from the audience. I will just here raise one of them, and any of you can volunteer to take this. Where do you think is the challenge managing chemical data for ML, AI, and pharma? Is it acquiring, integrating new tech and methodology, or recruiting skilled people to correctly interpret and prepare the data? Perhaps Esben or Andreas would like to take that? Yeah? Oh, Ted would like to take it? Sure.
Yeah, I can take some of that. So finding people who know how to apply FAIR principles, who understand things like ontologies and taxonomies and how you use those things, basically combining knowledge engineering with some domain expertise. It's pretty tough to do that sometimes. So that's a problem. The other interesting thing, and I mentioned it when I said there's a separation that people are looking for between data and systems. People are trying to actually not focus on those systems. Technologies, techniques, various specific applications will come and go, but the data will always be there. So the more attention you pay to them, the better off you'll be in the future.
I think it's both points. From my side, it's both points that were mentioned before, but also understanding which data do we need for which purpose. I mean, I know I'm repeating myself, but because only then, because you say that the data stays there, that's right for the current data, but which data we generate in the future, of course we can decide, right? And that is basically, I think that's very important in order for 10 years to be in a situation where we know which data is useful for which purpose, to understand that better right now, for the in vivo situation, in particular. I mean, that is very important as well, I guess.
Yeah.
Okay, I think that's all the time we have for today. Let's quickly share my last slide. I want to thank all of our panelists, expert panelists today for their time and expertise and insight. And I'd also like to thank all the attendees for joining us today. And we have our contact information shown here. If you'd like information about the Informatics Alliance, you can reach us at info@informaticsalliance.org. And a number of the representatives here also have their email addresses listed. We hope you enjoyed the panel discussion as well as the short presentations. And thanks so much for your time and have a great rest of your day.